Hello, my name's Roberto. This is my project. I decided to do it on breast cancer classification, and I found this data set on Kaggle. It is given by the University of Wisconsin. So these are this is data on breast cancer in Wisconsin. Um, so yeah, let's get started. So I wanted to find out, given this data, is a tumor benign or malignant? That's primarily what I wanted to find out. So we could split this data set up or look at new data and classify them from there. So these are some of the basic libraries that we'll be using: ggplot2 and plotly, obviously for plotting, dplyr and tidy for clean data wrangling and manipulation, and then ggcoreplot for also for plotting, and then caret to create our model that we'll get into later on. So if we look at our data, as we can see, it is breast cancer Wisconsin data. So this is like I said, from the University of Wisconsin. We have ID diagnosis, which is M, but if we expand it, it is categorical, so the values are M and B, and for malignant, B for benign. We have radius. This isn't so much important because each feature, if we consider only the first part, such as radius, texture, perimeter, area, smoothness, compactness, and etc., they have three values. So they have the mean, the standard error, so radius mean, radius standard error, and then their worst value, so radius worst. Mean is pretty straightforward. It is the mean of all the images combined. I believe it was 30 images together. So this is the data from 30 images put together. The standard error is the difference with amongst the images, and then worst should translate into the largest value. So radius worst is actually the largest radius found for that patient in that image, and this is titled worst because a bigger radius means that it is a bigger tumor, and that is something that patients do not want. So that is why it is titled as worst. So each feature appears 3 times: mean, standard error, and worst value or largest. If we look at the values themselves, we can see that we have 32 variables, almost 600 observations, and all of our features are numerical until we get to diagnosis and ID. ID is just an integer that each ID is unique to each patient, and then diagnosis M or B, categorical. So first of all, to get into start working with our data and creating our model and visualizing it, we want to make sure that our data is clean and that no missing values are missing. So we grab the sum of all data that is null. As we can see, the data, there are no missing values, which is great. And then if we visualize our data and we create a density plot, we can see the distribution for each variable. So this isn't so much important. This is just basic visualization, see what is high represented and what isn't. But if we look at how many of our values are benign and malignant, we can see that benign has over 400, almost 400 values. It is somewhere around 360, 370, and there are over 200 malignant tumors within this data set. So just represent the frequency of them. And so to keep our data uniform and consistent, we want to convert M and B to 0 and 1, 0 benign and 1 malignant, which is what we do here. So if it's malignant, we convert it to a 1 because that's bad, and if it's a 0, and if it's not, then we convert it to a 0, representing benign, because there are only 2 options within this column. So if we visualize our data through a matrix, through a correlation matrix, we can see that there's a lot of multi-collinearity that is best represented here, where it is 1 and then 0.99. And in my research, I found that standard values of 0.08 or higher represent multi-collinearity, which is bad because if we select both of these features, this is an extra dimension that is not really needed, and it doesn't represent more of the data. So yeah, this is what our correlation matrix looks like. The redder the area is, the more correlated the values are. Obviously, it's all red diagonally because they are the same feature. But we can see there's a lot of multicollinearity here between area worst and area mean. so yeah, a lot of the same area and area is highly correlated, even though they are not the even though they are different calculations. um, and then we can break this correlation matrix down because it is hard to see and hard to trace these values. We can break them down into mean, standard error, and worst, just to better visualize things. So here we can see that area mean and radius mean are highly correlated. This is pretty straightforward because radius is easy to calculate. Area, same as perimeter. Area and perimeter are highly closely correlated. So yeah, pretty straightforward. But for number one, we can see that there's a lot of multi-collinearity here. So for example, radius mean and perimeter mean very highly correlated, nearly the same value and whatnot. And then if we look at their plots, we can see that all the values are closely aligned together, whereas for example, compactness mean and perimeter mean, they are very dispersed. And we can do the same for the standard error, area standard error, and radius standard error. Once again, radius can be used to calculate area, so that represents that representation is pretty straightforward. Same here, a lot of multi-collinearity, just easy to look at. Once again, area, perimeter, and 0.99 and 0.98, lots of multi-collinearity here around. So what we want to do is standardize our data, scale it, and although this matrix did not do the best job of visualizing it, we want to, first of all, our diagnosis, we don't want to scale our diagnosis. We want to keep it at 0 and 1, not put it on the same scale as everything else. So for that reason, we scale every numerical value starting at the third one, which if we go back to our data, yeah, we want to go 1, 2, 3, start at all the numerical values. And although diagnosis is now numerical, we want to keep it at 0 and 1, which is why we do that. We don't want to scale that data. So yeah, and then you want to add in our diagnosis column back in, and then add that into our normalized data. And this is what that looks like. No value should change. No multi-collinearity does change here, except the axis of the data. We can see that it is now -2, 4, -2, 4, -2, 1, -2, 0, 0. 8 is the highest value. So the range is from -2 to 8, which is 10. Whereas if we look at the original unscaled data, we can see that 1,000 and 0.05. So there's a much bigger range on the unscaled data. So scaling it works better for our PCA analysis, right? And if we do that, a principal component analysis, we set scale equal to false because we already scaled the data. And although we could have scaled the numerical values too, meaning diagnosis. I mean, if we wanted to scale diagnosis, then we wouldn't have to scale it back here. We could just set this equal to true, but that is not the case here. And we want to center it around 0, which is just standard practice. So we can see that PC1 represents 44% of the data, PC2 almost 19, and then PC3 is 9% of the data. And we could stop at PC2 because we are going to visualize this later on, and we could have 2 dimensions. However, 72% is much better than representing 63% of the data, so we can do a 3D plot later on. So we want to extract those values, which will be our PCA components that we will use. And then this is for scaling it with the diagnosis column, so we can just see that we switched true, and then we implemented the second column as well, which is diagnosis. So our scree plot shows that PC1, PC2, and PC3 are our highest values. PC4, 5, 6, 7, 8, 9 are also very, very important. So going forward, or I guess without visualization in mind, we could choose PC1 through 9 to create our model. But getting into it, we want to convert our data from numerical to categorical. So we factor it, and then we'd want to do an 80-20 split on our data, 80% for training, 20% for testing. So that is what we did here. And then we obviously extracted the top 3 principal components, PCA components, which is the same code as right here. Just writing it again in case we need to change anything there, in case we want to do the first 2, not the 3. And then we tune our KN model with cross-validation, which is what we did here, CV. And we do a 10-fold cross-validation just because our data set is not so big. We have 600 observations, less than that. The higher the observations, the less folds, but lower the observations, the higher folds. And this isn't that big of a data set, so I did 10. And then in testing, which is not represented in this data, I found that k equals 4 for our KNN model was showing the best results. So I included that, which is why I did a step by 3, because 4 is included there. And no matter how high I set the values, the lower values were always better. So that's why I included 1, just in case 1 was better in this case. And then we tune it. Obviously, we train it on our PCA components, and then on our training set method, we want a KNN model, KN nearest neighbors, just because if we cluster them, that wouldn't make much sense. Rather, we want to compare it with the surrounding values. So we can see that our model is pretty accurate. That k equals 4 did return the best value, and then our accuracy was 97%. It is very important to show that 95% of our true values were selected, and then 100% of our true negatives were predicted accurately, right? So that's also very important. 95% confidence interval, meaning which is also something to consider in creating this model. And then if we visualize the data itself, we can see the training data set. So a training data set is everything in red. 0 are the benign tumors and 1 are the malignant tumors. We can see that there's a large cluster of benign tumors in relation with a higher PC1 value. So that's something that's very notable. And then if we consider all the testing on the benign and the training data set, we can see that the training data set does represent outliers pretty well, which is good in case our testing data set has any as well. And if we compare that with the malignant tumors, that is not the issue, because malignant tumors are closer with a higher PC2 value, obviously because there are much more malignant tumors above it than below. So that is something to consider as well with our model. So overall visualization, we can see that here. Going forward, I don't think that this was the best model to choose from, but I did want to include a PCA analysis. But however, going forward, I just do a random forest, because that can random forest without visualization, because that way we don't have to worry about choosing just three dimensions. Rather, we can choose many more, and a random forest is very good at taking in many more dimensions. So going forward, I would like to do a random forest analysis, but for now, this is my PCA and KNN. Thank you.